Thank you. Good afternoon, everybody. So, yeah, I'm Federico, Senior Research Fellow at Ulster, and I'm presenting a case study in using lightweight language models for risk-controlled self-assessment. But let's say that in general, this is a case study presenting how we can use lightweight models for domain-specific problem. So this work was framed within the Advanced Research Engineering Center. I'm co-investigator in this partnership between PwC, Ulster University, and Queen's University. We are looking at themes like generative AI, natural language processing, explainable and trustworthy AI. And in particular, among the trend topics of generative AI, I will touch on light language models, user-in-the-loop AI, and indirectly hallucination management. So first I want to define some terminology that will be useful to distinguish the two types of language models I'm going to present. So in our communication between a speaker and a hearer, we can define competence as the understanding of the speaker and the hearer of the language, of what is being said. And we can define performance, the actual use of the language in a concrete sentence, in a concrete situation. This definition comes from linguistics. It's a very old definition, but still it's useful to understand different characteristics of models. I'm not entering the debate between language versus intelligence, but let's say that language models, we can say that language is part of intelligence, but yeah, as has been said, language models do not think or distinguish right or wrong or false from true. So recently within AI, the attention has been drawn to generative AI and large language models, and in particular at the intersection of these two. So here we are talking about very large architecture, so billions of parameters, hundreds or thousands of billions of parameters. And these models can generate text. So we can say they are performance-oriented, going back to the definition I just presented. But what about other types of language models? So there are, for example, a subset of non-generative language models, masked language models, that are way smaller. So we are talking about 100 millions of parameters. They cannot generate text, but they are performance-oriented. So that means they can still understand and can be used to analyze text, better said, or analyze the quality of text that has been written. The fact that they can generate text is a limitation, of course, but let's consider there's a lot of existing data that needs to be processed. We do not always need to generate text, and not all tasks require text generation. Plus, I'll show you that there's a way of using these models even when we are generating new text, if we keep the human in the loop. How did we get to language models? Very quickly, to understand the differences between the two models I'll be talking about. So it started with Word2Vec, which was an attempt from Google to represent concepts as a numerical vector in a vector space where similar concepts goes together and opposites are far away from each other. And you can perform mathematical operations on this vector space. So it's brilliant. You can take Paris, you can subtract France, and get the concept of a capital. If you add Japan, you get Tokyo. Perfect. But what about Paris, the Prince of Troy mentioned in the Iliad? Of course, that representation of Paris won't be that good in a different context. And that was the limit of these kind of approaches. Glove was something that came just after Word2Vec. They are both based in co-occurrences. So you take a lot of text, analyze how often words appear together in the same context. So you can preserve the fact that Paris often appears with France and also sometimes appears with Ellen, as in the Iliad. But this representation is not able to tell you which of the two meanings we are actually seeing right now, because it's a static representation of concepts. And this is where language models actually made the difference, because they create this representation based on the context in which each word appears. So we can use them for a number of tasks: translation, summarization, classification of text, and we'll see some examples. So I mentioned there are two types: performance-oriented and the generative ones are the ones that are performance-oriented. So the first phase in which they are trained to predict the next word of the sequence. So that's what they do. They don't reason. They're just trained to predict what could be the most likely word to continue the conversation, the text that is being analyzed. And if you can predict the next word, you can predict the next and the next, so that means you can generate text. Trained on sufficiently large amount of data, they're very versatile. They seem to be able to reason. Actually, they're mimicking the text that is being used to train them, but let's say they're very versatile and useful. Cons are, of course, hallucinations, because they don't know if what is right or wrong or true or false. They're just trained to produce what's more likely to be the continuation of the topic. Masked language models, instead, they're trained not to generate text, but to fill a masked word. So taking a sentence, you delete part of the sentence, mask some of the words, and you train the models to reconstruct. So there is a fundamental difference between the two, because in the first case, the encoding of each word goes from left to right, because you are dealing with an open sequence. There's no other way of doing it with an open sequence. So each word depends on the context that appeared before the same word. Here we have the complete sentence when we represent each word. That means you can use the bidirectional encoding, so the context before and after the word. That gives you better chances of solving the anaphora problem, which happens every time we have a pronoun that refers to a subject that was previously mentioned in the text. It doesn't mean that ChatGPT is not able to solve the anaphora, but masked language models can do it with smaller architectures, with a fewer number of parameters, essentially. And this is what Google uses now to answer your search queries. So BERT is a masked language models, and that's why you can ask questions now to Google, and it'll find you better answer than the old approach using keywords. So you can ask questions like this one: can I pick up a prescribed medicine for somebody else? So let's consider these two again, these two types of models. So we have generative language models that we said that they're very expensive, they're very large, so they require expensive hardware to run. And that means often they are external services, which brings also a privacy issue, because if they are external, you need to share the data with OpenAI or an external company. At the other end of the spectrum, we have lightweight models. They cannot produce data, but you can use them to analyze existing data, for instance. Confidentiality is not an issue, and you maintain ownership of the model if you take an open source one and fine-tune it for your problem. Few applications that are very useful of this type of models, like question answering for information retrieval. So given a piece of text as a context, if you have a set of questions, you can use these models to find the portion of text that is most likely to answer your question, and also identify if the answer is not there, which is what we used in our case. And you just use this ability of language models of representing text as numerical vectors. And you see it now, the trend is using retrieval augmented generation that actually combines the two types of models. So you have a retriever model that usually is a non-generative language model, and then you have a generator. And you can see some examples, like if you use some search engines, you see this is an example of a mixture of the two models in which an answer is generated, but on the basis of text that it's taken from the first results of the search. And this is an example of a non-generative use. So it will just highlight the portion of text that answer your questions from the first result of the search. So we used it in a risk control self-assessment case in which we needed to analyze descriptions to check if they were compliant with regulations. And to be compliant with those regulations, they need to contain certain pieces of information: the description of the risk itself, what are possible consequences, the probability, possible control measures, and so on. And we use the question answering approach on this risk description to check if the answer was there or not. Initially, we used generative language models to produce a set of synthetic risks that were validated by an expert, so we were sure that these were representative of real data. And we did that to avoid using any risk from any of the customers of PwC. That was the partner in this project. So we tested one of these lightweight question answering language models to ask questions like, what is the risk, what are the consequences, and check if the answer were there in the description. Results were not too good with a general purpose model, but after fine-tuning on just a few hundred examples of risks, actually results were good enough to try and test the model with real data. So now we can use the model to check compliance of real data, and we can also enable a reinforcement learning feedback loop in case the model gets something wrong. So this is a short demo of the implemented risk language model. So there was an audio on this video, but yeah, well, subtitles will help you.
Fields are mandatory, then start typing a risk description. The RLM analyzes the entry in real time, verifying which information are present, and more importantly, which are missing. The model has identified risk, condition, and probability, and now suggests adding the consequences.
So we can also use these models when we are generating text, if we keep the human in the loop, and that will help them to make a better job faster.
The consequences have been identified. The RLM now recommends adding a control measure. The risk description is now compliant and can be saved without the risk of being incomplete.
And of course, if you can process one record in real time, you can analyze existing data in bulk. And you can extract statistics from the existing data, and that's what we tried.
The cumulative statistics summarize the main indicators, the percentage of compliant, non-compliant records, and the distribution of the most common missing fields. This functionality allows the analyst to quickly assess the quality of pre-existing records.
So we have seen that we can use a lightweight model, non-generative, either when we generate text if we keep the human in the loop, and we can use it to analyze existing data to check their quality. Of course, we wanted to check also how these were performing compared to a generative one. So GPT-4, we tested Claude 3, and also some of the smaller ones, like Mixtral. It's a generative model, but it's way smaller than Claude and GPT-4. And you can see that there were different accuracy for the different fields, but in average, they were all about 90% with some differences that are not statistically significant. So we can say that we could reach the same level of accuracy with a lightweight model, which is way lighter and more sustainable than the others. And to give you the benchmark information, electoral arch was actually the base of the model we used before fine-tuning. So you could see that from 55%, we reached 90% accuracy, which is comparable to two larger models using domain-specific data. So if we want to use a lightweight model for a domain-specific problem. So yeah, we pretty much got there, and we see that results is even better than what a 7 billion model can do of the generative type. So, and there's another issue with using generative models, which is repeatability. So we notice this kind of behavior when using GPT or Claude. Same risk description, you run the data twice through the model. First time, the risk is interruption of service and the consequences are not found. The second time, risk is power outage, and the consequences are interruption of the service. Now, here it doesn't matter which is the right option, but you prefer a model that behaves always the same way. You want it to be consistent with the previous answers. It's been already integrated into RiskLink, which is a project under development in PwC, so this has been integrated as part of the risk control self-assessment PwC is working on in collaboration, PwC UK and PwC US. So this gives us some time to stop and reanalyze the two approaches. So we mentioned performance-oriented and competence-oriented model, lightweight model, larger architectures, larger models. If you want to have an idea of how larger, those are numbers. Those are the numbers for GPT-3, I believe. So GPT-4 is even larger than that. And already gives you the scale, because 2 gigabytes in size of the model, it means you can even run it locally on a laptop. It doesn't require like expensive hardware to run. Of course, versatility. ChatGPT, you can use prompt engineering to make it solve new tasks and problems without any fine-tuning. But if you need to fine-tune, a model like ChatGPT is going to be extremely expensive, while a lightweight model, in our case, it took less than 3 hours on one GPU to fine-tune a general-purpose model to a risk language model. Hallucinations are not possible because it doesn't generate text, so it can only point you to the content that answer your questions if it's there. And then there is the fact that it doesn't require to share data with third party. That is required if you use the OpenAI or Anthropic solution. Of course, yes, you could have an agreement with OpenAI and have GPT installed in your own network if you can afford that. But it's going to be very hard to deploy GPT instances in all your customers' network if your customers want to keep their data confidential. And that's something we can do with a lightweight model. We can even deploy it as an installable application and would run on a normal laptop with 16 gigabytes of RAM. Not for fine-tuning, of course, but you can use it for analyzing data. Cost, of course, it's way cheaper to run on hardware which doesn't require massive hardware. And that cost, of course, is the API cost for ChatGPT. That, of course, includes maintenance costs that you need to consider if you develop your own lightweight model. In terms of accuracy, we have seen that you can reach a comparable level of accuracy, and energy consumption, of course, is way in favor of a lightweight model. So sustainability is also important, is an issue, and something we need to consider. But I want to close with what I believe is one of the most important aspects here, especially for businesses. What about the intellectual property of the solution you build? Because if it's your fine-tuned model, domain-specific problem, you keep ownership of the problem. If you build a solution based on Anthropic or OpenAI API, in essence, you are sharing with them the IP of your solution. Plus, your solution depends on a sole vendor. If they decide to increase the price of their API, your product will be affected by that. So that's it. That's our experience in ARC and how we used a lightweight language model for a domain-specific problem.